Zero core depends on just one small external library called Izumi-Reflect. And it's an independent implementation of TypeTag for Scala. And in this talk, we are going to learn how this library works and have a look at the Scala type system from an unusual perspective. We only have about 20 minutes, so it won't be possible to consider every aspect of the library, and we will concentrate on the most curious parts. I hope you're gonna enjoy this, and in case something is not clear, please ask your questions after the talk. And first of all, let me introduce myself. My name is Pavel, and I'm from Septimal Mind, an Irish software development consultancy. And we are focusing on engineers' productivity and team efficiency, and we are big fans of Scala and pure functional programming. Also, we are participants and contributors of different Scala projects. So, Izumi-Reflect is a compile time reflection framework, a portable replacement for Scala Reflect. It's a tiny library which essentially for any pair of types can answer just two questions. Is one type identical to another? And is one type a subtype of another? Of the other? That doesn't sound like a big deal, but in fact, just the ability to answer these questions at runtime opens us endless possibilities and allows us to safely implement many important patterns which truly improve developer experience and productivity. So, Izumi-Reflect powers modern implementations of creational patterns. It's the cornerstone of ZOZ layer, the service locator mechanism of ZO, and DStage, the dependency injection library for pure functional Scala. Unlike Scala Reflect, Izumi-Reflect is thread safe. It works on virtually all the possible platforms for Scala code, and Izumi-Reflect supports Scala 3. It's important to note that it's possible to combine Izumi-Reflect tags at runtime, unlike Scala Reflect tags. So before going further, we should define what a type is. Many of us learned this concept intuitively. And for this talk, we would use the following definition. A Scala type is a value in the compiler heap during compile time. It's bound with elements of abstract syntax tree and defines their properties and restrictions. So we may say that a type is a tag for some syntax tree elements. And the reflection is a mechanism which allows us to access type information during program runtime. Reflection requires type information to be captured during compile time and then serialized as values accessible during runtime. Unlike Java reflection, compile time reflection in Scala may be precise. Not bound by the rules of type erasure. It may be funny to note that, in fact, Java reflection may be called compile time reflection too, but only for Java types. It's not always easy to distinguish compile time reflection from runtime one, because if some compile time information leads to decisions made at runtime, that probably should be called a runtime reflection. And in that sense, Izumi-Reflect is a runtime reflection mechanism, though it extracts and prepares type information during compile time. In that sense, it's a compile time reflection mechanism. So Scala Reflect serializes big chunks of the compiler state, and it uses the actual compiler in runtime in order to process type information. This approach provides precise answers, but is hard to implement and maintain, error-prone, works only on JVM, and the worst thing, it doesn't work on Scala 3. Usually reflection is used to either build heterogeneous maps or to find the exact type of a value where only the base type is known. That's what the layer does. We also found a very cool and powerful pattern where we attach arguments and output tags to a lambda. Then we may introspect such lambdas at runtime and, for example, build directed graphs out of them. That's the core idea behind this stage. We call such extended lambdas functoids, and they are really cool and have many useful properties. So the idea of a macro level compile time reflection for Scala is simple. First, we need to create a reasonably simple model of Scala type system, when inspect Scala types with a macro and represent them in terms of our model. When we need to serialize these instances for further inspection at runtime, and when implement a limited model of the Scala compiler itself. A simplified typer simulator, which would process the values we stored at runtime and answer our questions. Though there are multiple challenges along that way, the Scala tree developers themselves considered this problem to be too hard to be solved at macro level. At the same time, they declared that they won't implement any alternative to Scala Reflect because of the complexity and the necessary trade-offs, so we actually had no choice but to do it on macro level. So the most important questions are how we model Scala type system and how do we model the relevant parts of the compiler. And also we have to consider the fact that nominal inheritance is strange and perplexed, and one might say that there is some unsoundness in it. And we need to learn how to deal with that. I'll say more on that later. Also, there are numerous technical issues, considering that the macros have limited access to the type information and the internals of the compiler. We cannot just dump compiler data structures as Scala Reflect does. And Scala syntax trees themselves are very, very complicated. Now, let's talk a bit about Scala types. And there are many classes of the types, and this is kind of a joke. So the most important of these classes are are proper types. So proper types, they describe some values which may exist at program runtime, like an integer, a string, or a list of integers. And another important class is type constructors, which are used to construct our types, usually by applying arguments to the type constructor, like a generic list is a type constructor. A type constructor which accepts another type constructor is called a higher kind of type, and such types they create another important they form another important class of Scala types. So proper types can be basic or applied. Applied types are just fully applied type constructors, like a list of integers is an applied type obtained by applying list type constructor to basic type integer. And basic types are, well, some basic things we used to deal with, like built-in types, non-generic classes, etc., etc. There are also our proper types like intersections and unions, but let's not concentrate on them too much. The diagram on the screen shows the approximate taxonomy of Scala classes. Now, let's think how we may represent a basic type. Essentially, it can be represented just by its fully qualified name. So if we say that we talk about Java lang integer, just that name should be enough to exactly identify what we are talking about. And we don't need to preserve all the data structures associated with it within the compiler. We just need the name. So we may define a sealed trait called reference that stands for type reference. And create a case class name reference with the trait and with a string field for the fully qualified name. And this would be enough to represent basic types. The actual implementation would be more complex because path-dependent Scala types may have prefixes, so we would need a field for that. And also, if we wish to use our name references with type constructors, we would need to define an our field to store type boundaries. And this is an odd deviation from Scala model, but it's very convenient for our purpose. Now, let's model applied types. An applied type may be represented by a fully qualified name of its type constructor and the list of its parameters. And now comes our deviation from Scala model. We represent a type parameter as a type reference plus the variance of the original argument of the constructor. And this is odd, but it allows us to always have the variance data exactly at the place where we need it and keep our model tiny. As with basic type, we would need the prefix for applied types. And now the tricky part starts. How do we represent type constructors? We may use a notation alike to lambda calculus. This is not what we usually call lambda calculus because we support multiple parameters in function definitions. So let's assume that type constructors consist of two parts, the arguments list and the return value, which may be a proper type or another type constructor for higher kinded types. And when we apply type constructor to its arguments, we just need to recursively replace every type placeholder from the parameter list with its corresponding value. So there are some examples on the screen. I have a type constructor K with two parameters A and B. This type constructor produces a proper type by providing either, which is actually a type constructor itself, two arguments, B and A. I'm using annotation. I'm using a specific notation to write down such things. And actually, I think this notation should be obvious and clear. Higher kinded type T is a bit more tricky. It itself accepts a type constructor. Though for our purpose, we use something alike to untyped lambda calculus. So we just ignore the kind restrictions on the parameter f. So we may write down type T as a function taking one argument and returning applied type T parameterized by that argument. Remember that this is just a notation allowing us to write down type constructors in more readable form. Now, what happens if we apply type T to type K? The result would be a proper type obtained by applying type T to the corresponding type lambda. Note that we use additional disambiguating indexes on the lambda parameters. And that is an imperfect normal form, which allows us to write down lambdas in a more or less unambiguous way. And also, it allows us to use the written form for identity checks. Though this is not a true normal form, it still allows ambiguities in some edge cases, and it may need additional processing for identity checks, while true normal form should be unambiguous and should allow us to compare just the written forms for identity checking. There are several possible normal forms, and it's not easy to choose the best one. So with that said, it's easy to write down a model for type constructors. That would be just a list of strings as input parameters and a type reference as the lambda value. The parameters should be referenced somewhere inside the output of the regular name references. We would also need to represent intersections and unions, and in fact, where representations are trivial, where just sets of references. Also, we will need to represent structural refinements, and that's the odd thing, the wildcard type. sorry, and the odd thing, the wildcard type. But that would be outside the scope of our talk. Anyway, trust me, these entities are actually easy to deal with. So at this point, we may say that Scala types can be represented with a simple recursive data structure. And this representation, it would be imprecise. It won't match Scala model, though it would be enough for the purpose. The good thing is that it's certainly possible to convert Scala types into our model using just macros. But we still need the rest, the runtime code, which would be able to process our values and answer the questions about equality and subtyping. So the key to the type introspection is a method called base classes, which is defined for type representations in both Scala 2 and Scala 3. And this method allows us to enumerate the supertypes of a type. But the question is what we actually need to store to be able to apply our type constructor representations at runtime and inspect the relationships between combined types. So first of all, for each type we encounter, we store all its supertypes in applied form. And that is logical and it really makes sense. Though that's not enough. We also store relationships between types without their type parameters. So for a list, we remember that it's a type. We remember that it's a subtype of sequence, iterable, etc., 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 up to object. And such relationships are very odd. Very, very odd from Scala point of view, but we are truly useful for the purpose of subtype checking in our simulator. So that's what we need to store for a tag of a list applied to an integer. These screenshots are taken. Actually, these are the screenshots of our debug output for Scala 2, and you may notice that there are some irregularities. So, as I said before, our model, it deviates from what Scala does, but it works. So the typer simulator, which checks inheritance, is just one big function, which carefully considers all the possible pairs of the references and applying corresponding rules. So, for example, if we want to know if a type is a subtype of an intersection type, we should check that that type is a subtype of every member of the intersection, etc., etc. Some rules are easy to write down, but computationally complex. It's funny, but computation complexity for subtype check of two union types is quadratic. We don't have enough time to walk through all the rules, so if you're interested in that, just follow the link on the screen and check the actual code. So, as I said before, inheritance is somehow perplexed. The user may ask our little typer any questions, and we should be able to answer in a reasonable manner. But some of these questions may make no sense from Scala point of view. And that is especially true when we need to check relationships of two lambdas and a proper type and the lambda. Probably A generic list should never be considered a supertype of a list applied to an integer. But this is one more of the horrible deviations from Scala logic we allow in our model. It's interesting to note that Scala and Scala Reflect themselves do not allow to compare types of different kinds easily. Some dirty tricks are necessary if you want to do it from outside of a macro. That hides the complexity and strangeness of inheritance, but well, it's still there. So we considered the basic ideas behind Izumi-Reflect model of Scala type system and typer. There are multiple other complicated aspects, but they are not fundamental and not that important, so we omitted them in this talk. As a conclusion, I would say that Izumi-Reflect is a powerful compile time reflection tool for Scala. It's stable, it may help you a lot. Feel free to use it in your projects. Don't worry that it's imprecise. In fact, it's very good for most of the practical users. There is still a lot of work to do. Your contributions are very welcome. And if you decide to make a contribution, of course, we'll help you to get on board. So Izumi-Reflect is a complex tool and an important part of the ecosystem. We invested a lot of time and hard work into it, and we would welcome any help, especially pull requests. So thank you for listening. If you wish, you may check our other projects on GitHub and subscribe to our Twitters. And you may also sponsor the further development through our GitHub sponsors page or just buy us a coffee.